Hello and welcome to all my viewers and all my students who are following me on this YouTube channel. Today I'm here with a new topic that would be helpful for all those who are about to start their viscometric studies. I'm Professor Dr.Mchem from Dr. Mchem Institute of Chemistry, University of St. John, Shiro. And I'm here again with something new, something very interesting, something very, a topic whom I have worked on for a very long period of time. So let's talk about viscosity. So what is viscosity? Viscosity is simply internal resistance of, a liquid to flow, right? This is simply called it something that resists a liquid to flow. This is simply called resistance. Some sort of a resistance is there which prohibits liquid when it's in the flowing process, right? It happens when it's in the flowing process. Now, if we talk about the polymers, right? If we are going to, find out viscosity of a polymer, or if we are discussing, you can say a dilute solution viscosity for the polymers. So how one could achieve that goal? So keep that thing in your mind that whenever after the synthesis process, when you come to this physical property called viscosity, and you're about to calculate the viscosity of a polymer, the polymer has to be essentially be characterized thoroughly before it could be processed, or you can say utilized in the polymer industry. Now, what is the characterization? Of course, the characterization involves to resolve number of different significant features like, of course, polymers, the molecular weight, shape, size, and its molecular size and structure, and that would provide a useful and complete information about the macromolecule. So what is viscosity? Viscosity is fluid's internal resistance to flow and is considered as, you can say, as a measure of a solvent's resistance. Okay, so now I will be discussing with you the dilute solution viscosity measurements that can be determined by Oswald's viscometer. Now, Oswald viscometer is a very simple instrument or a simple glassware, apparatus that from once you have learned to calculate, measure the viscosity, you will be able to find viscosity of different, solvents by using this typical Ostwald viscometer, and simply you have to calculate the flow time between the two parts that are there, that is the starting upper part and the lower part. There's a, it's a U-shaped instrument, and in which I'm going to show you in one of my slides, and you are going to measure the flow time of the solvent when it starts flowing from the upper mark and to the lower mark, right? So you, with the help of a stopwatch, you will start and you'll start the stopwatch when it starts flowing from the first, the upper mark, and you will end up when it touches the lower, that meniscus, it touches the lower mark, right? So that flow time will be able to tell you about the, how much time in seconds it took, or in microseconds it took in flowing from that to that part, right? From the upper mark to the lower part. So the measurement of each concentration and temperature was made 3 times. Now you have to make 3 times. You will record that. Briefly, I'm explaining you how you're going to use this Oswald viscometer. So this would be done. The measurement at each concentration, and there will be different temperature regions starting from 283 degrees Kelvins to others, so on. So each concentration temperature was made 3 times. You have to take 3 times, and extensive care and concentration will be provided because on the vertical position of the capillary that is inside the viscometer, right? So you have to you have to be very careful when you are doing the adjustments regarding the vertical position of the capillary. The capillary has to be vertical in the direction. When you will clamp your viscometer with the stands, the capillary position is supposed to be, notice that is it in the vertical, or there shouldn't be any it should be vertical at that moment. So that was one of the points that is supposed to be regarding. Okay, and the temperature will be monitored of that viscometer with the help of a Gallen-Camp thermostatic water bath, right? We'll be using a thermostatic water bath that would be providing the temperature, would be providing the monitored temperature So what is now dilute solution viscometry? If you discuss about dilute solution viscometry, is dilute solution viscometry? So it simply calculates or computes or you can say estimate the relative viscosity of dilute polymer solutions, right? So it will simply tell you about what it's going to tell you. Of course, it's going to tell you it will compute or it will estimate straightly, right, the relative viscosity of the dilute polymer solution. And of course, the other few types will also be calculated, like inherent viscosity, intrinsic viscosity of the polymer material. So I will be starting with you with my presentation, which I prepared few slides for you so that you will be able to understand and follow what I want to tell you right now. So let's discuss that thing first. Okay. So I would be happy to share the slides. Okay, so there we are. As I just mentioned, we're talking about today viscosity. So viscosity of dilute solution polymers, I just mentioned. So I would be discussing with you the introduction, of course, the definition, and parameters to calculate viscosity. These are the three topics I have chosen today for today's topic. For calculating or for understanding what is dilute solution, viscosity of dilute solution, viscosity of dilute solution of polymers, right? So let's start with the introduction. So as I just mentioned, each and every polymer should always be characterized before it could be processed further to the polymer industry. So what is viscosity? Of course, viscosity is defined as the internal resistance of a liquid to flow, simply, right? Viscosity simply opposes to flow. It opposes to flow, right? Its opposite is fluidity. Yes, of course, that's the opposite of its viscosity, fluidity, referring without any effort to flow. It wouldn't be having any resistance to flow. That is fluidity. So now, dilute solution viscosity of monomers and polymeric compounds can be carried out by using Oswald's viscometer. So yes, of course, we can find out, we can calculate, we can compute the viscosity of monomeric compounds. We can, compute the viscosity of polymeric compounds, polymeric resins, by using this wonderful instrument called Oswald's viscometer, which is U-shaped, right? And it has got two bulbs. We can refer it to A bulb and B bulb, and the solution is filled inside it. Whatever whose viscosity you are supposed to find out, you will fill that. But before that, you need to go through different steps. That is, of course, as I always, it's made up of glass, so you need to wash it properly, and then you are going to, of course, rinse wash it with a distilled water, of course. Then, of course, you will be washing it with chromic acid. Now, what is chromic acid? I will tell you. And then, of course, you will be, washing it with the ethanol, right? And then you will dry it, and then it would be ready to use or ready to compute your viscosity. You will fill your water inside it, because you need to calibrate your instrument before you carry out the other measurements. So you need to calibrate the viscometer first. So which I will explain to you in my next lecture, how you're going to calibrate your viscometer, the calibration of a viscometer will be done, right? So that I will explain to you in my next video. Okay, so now the best examples for analyzing viscosity are water and honey, as you can see here. Now you can see the consistency of course, honey, the flow of honey, right? It's viscous. That means there is a lot of resistance between the molecules that are holding each other. The molecules are resisting each other, and they are resisting the flow, and they are resisting, the way they are flowing, the molecules are resisting each other, they are pushing each other, they are forcing each other not to move fast. Whereas if you flow, if you simply see the, flowing of this water, see the consistency of water and of course the flow. Yeah, of course, it just goes into the from one container to another within no time, right? So its consistency is nothing as compared to honey. So these are the best examples. Always, they are everywhere on net, on Google, everywhere they are. This example is quoted for measuring viscosity. What? Of course, water and honey. Okay, so if we now talk about the viscometer, how does it look like? This is a simple diagram. I have drawn it. So just to make you understand what does this Oswald's viscometer looks like. It's all for those new students who have not gone through, the measurements of by using this Oswald's viscometer. So I thought that I must share with them today this instrument. I must tell them how does it look like. So it's has got two arms, that is arm 1 and arm 2, and now there are you can see there are two lines here. There are two marks, the upper mark and the lower mark, right? So time is noted as liquid. You will fill this, right? It will be filled, and then time is noted as liquid flows from upper to the lower mark, right? You will be calculating, you will be monitoring that time with the help of a stopwatch. You will start the stopwatch when it starts flowing from the upper mark, and you will stop it when it will reach the meniscus. It will reach it, and then you will stop it, right? So at least 3, now here I've written at least 3 or 4 readings are taken, and the mean of the 3 readings will be calculated, right? Okay. So this is Oswald's viscometer, right? It is U-shaped. You can see it's U-shaped. It has got 2 bulbs, that is bulb A and B. Okay, here I've written something which I've just explained before, that after cleaning with the chromic acid and then with, of course, distilled water and then with acetone also. Yes, you can use acetone or ethanol for rinsing. Rinsing it is filled with a suction pipette. It is now how you're going to fill it. Yes, you have a suction pipette. With the help of that, you can fill the viscometer, right, easily, and then is allowed to flow from the upper mark to the lower mark, and time is noted by the stopwatch, by a given stopwatch of a given solvent. That is mostly, what is that solvent? Of course, water is the solvent mostly. So bulb B regulates the hydrostat. What does this bulb B do? Here you have, you are calculating the flow time from upper mark to the lower mark. From upper and the lower mark, you're going to calculate the flow of your flow time of your solvent, whatever solvent you are, analyzing. Whereas this bulb B, it regulates the hydrostatic pressure during the flow. The pressure that is developed between it, that is called the hydrostatic pressure. It will monitor that pressure. It will regulate that pressure. Okay, fine. Now you need to find out the density of your solvent also. So how you're going to find out the density? That is also very important parameter. In my next video, hopefully I will explain you how to calculate density and or specific gravity. We use a small bottle that is called a pycnometer, right? And pycnometer, how does it look like? It's a small size bottle, almost of 20, you can fill it 25 ml solvent can be adjusted in with a stopper over it that has got a very fine capillary over it. So you can calculate density of your solvent, right? With the help of a formula called density. You will denote density, and of course every typical topic has some typical terminology. So here, density is simply denoted by rho. Rho, this is rho, right? Rho equals to mass upon volume, right? Simply this is density's formula. Density equals to mass upon volume. And how you're going to denote density? With a rho. Rho equals to mass upon density. So today I'm not discussing density with you right here in this topic. I'm not going to discuss density. I'm discussing only the types, introduction types, and of course the parameters to calculate dilute solution viscosity of the polymeric compound. So today we are going to, and what are the different parameters which we can use to, calculate viscosity right? So let's proceed. So this was a simple diagram, or my diagram, well, I can use other, softwares to draw it, but by drawing with a hand, you can make other person understand more accurately, as compared to the ones that are already there on the net. So this is something interesting. And you do not keep this viscometer like when you are measuring on the table. No, you have to clamp it down. You have a clamp, you have a stand, iron stand, and you are going to clamp it, an upper clamp and a lower clamp, and you are going to hold, and this arm is, this side of the arm is clamped between, those on the iron stand properly, because it has to be fixed properly. And this, what I was telling about the adjustment of the capillary, this was that capillary that is supposed to not to be tilted. A little bit tilt is not allowed. It has to be straight. This capillary position is supposed to be vertical. When you have clamped the viscometer on the stand, it is supposed to be all vertical, right? There, it shouldn't be a little tilt seen, right, or being done at that time. You have to be very careful when you are doing the adjustments regarding the capillary position. It is supposed to be vertical, right, because you are doing a very sensitive analysis, that is, you're calculating the flow of the liquid when it starts flowing from the upper mark to the lower mark. Fine, let's jump to the next slide. Okay, now as I just mentioned that honey is more viscous than water. By measuring the flow time, one can easily figure out the time difference between their flow, right? Honey possesses large viscosity and therefore resists motion, whereas water is thin, having low viscosity. This I have already explained, that definitely it's more viscous, right? There are molecules that are resisting each other, that are forcing each other not to move with the fluency, right? And yes, so that is, and whereas as compared to water is thin, having lower viscosity. Naturally, that is obvious that it is its consistency is very low, and it has lower viscosity. Okay, now let's come to some viscosities, other aspects. The unit of viscosity in SI system is Newton's second per meter square. Okay, Oswald's viscometer or glass capillary viscometers are used mostly in measuring viscosity of a polymer compounds. Molecular weight can be calculated along with the size of the polymeric material by computing viscosity of polymer solution. So the molecular weight can also be, calculated as depending upon the size of the polymeric material. Okay, when we are computing the viscosity of that polymer solution. Okay, now let's see the parameters that we can calculate to calculate viscosity from flow time of solvent and solution, right? You have a solvent and a solution, so you can calculate the viscosity, right? So what could be those different types? Let's discuss number one, relative viscosity. Now this is number one, this is relative viscosity. It is denoted by, now viscosity here is denoted by eta. This is eta, right? So relative viscosity, eta relative. It is denoted by eta relative. And it is simply defined as the ratio of the solution viscosity, eta, to that of the solvent, eta naught. This is eta naught, right? That is eta, and that is so. What would be its formula? Can be calculated by the formula eta relative equals to eta over eta naught. And for dilute solutions, eta relative equals to T over T naught, where T, what is T? What is T naught? T and T naught are the flow time of the solution and the solvent, right? Then, as I just mentioned, you will calculate the flow time. So this T and T naught, what are these? These are the flow time of the solution and the solvent. Okay, this was something you can say a brief knowledge about relative viscosity, one of the parameters we are discussing today. Okay, let's discuss the other one, the specific viscosity. It will be denoted by eta specific. You can see here eta specific. It is the relative increase in the viscosity of the solution over that of the solvent. Release, it's simply, it is the increase of the in the viscosity of the solution you are analyzing over that of the solvent which you have made that solution, right? And it is, I mean, you can find it with the help of this formula. I have formulated this formula, and I have made it for you people to understand. So eta specific, that is specific because viscosity equals to eta minus eta naught O upon eta naught, right? Which is again equals to eta over eta naught minus 1, right? Now, in the above equation, we have seen that eta relative equals to eta over eta naught. So eta specific equals to eta relative minus 1, because here above we have already seen that eta relative equals to eta over eta naught. So from here, eta over eta naught, instead of writing that, we can write it down, eta specific equals to eta relative minus 1. And I have written also here, since eta relative equals to eta over eta naught. So now we have a formula to calculate specific viscosity. Eta specific equals to eta relative minus 1, right? This is how you can calculate your specific viscosity with the help of this formula. Whereas relative viscosity can be calculated from this formula, the above first one, and this from the second one. Okay. Well, viscosity is tough, but it's very interesting also, and I just love this topic. So I thought that I must share with my students, whoever is interested in nowadays calculating viscosity, whoever is, using viscometers, or whoever is using Oswald's viscometer, they would be, find this video helpful, and they would maybe they will these calculations or these formulas would be helpful to them when if they are finding the viscosity of the dilute solution. If they are performing dilute solution viscosity measurements. Okay, so third number is your reduced viscosity, and it is denoted by eta reduced, right? Eta reduced. It is the ratio between specific viscosity and over concentration, right? That is concentration. What concentration? Of the solution. Concentration of the solution. It is simply, you can see here, eta reduced equals to eta specific over C. Whereas if we talk about the fourth one, that is inherent viscosity. Now, in this one, in reduced viscosity, you will draw a graph, right? Between, reduced viscosity and concentration. There is going to be a graph there, and you will find out, some other parameters also. There is intrinsic viscosity, slope, intercept. These all things will come under this category, which I will explain to you in my next video, how you will calculate the reduced viscosity, right? Okay, because right now I'm just explaining you the different parameters through which you can, these would be helpful in calculating, the viscosities. Inherent viscosity, it is denoted by eta inherent. It is the ratio of the natural log of the relative viscosity and concentration of the solution. So eta inherent equals to log of, that is natural log, eta relative upon concentration. By applying this formula, you will be able to find out eta inherent. Now here again, a graph will be plotted between eta inherent and concentration, right? There's going to be a graph, and it will convey something to us. Fine. Okay, number 5th, intrinsic viscosity or limiting viscosity. You can call it intrinsic viscosity, and you can call it limiting viscosity as well. So it is denoted by eta. Here you can see eta is there. It's the measure of volume occupied by polymeric compound in infinite solutions, right? And can be calculated by Huggins and Kramer's equation. Now, what is Huggins? What is Kramer? Now, Huggins and Kramer's were the two scientists. So, formulated these two equations. Now, as I just mentioned it before, that you are going to plot a graph between eta reduced and concentration, and eta inherent and concentration. So, this is the same thing here, they are explaining that these are the two equations. And via these two equations, you'll be able to calculate different parameters. For example, eta reduced equals to eta plus Kh, that is Huggins constant, eta square C, that is concentration. This is Huggins equation, whereas Cramer's equation is eta inherent equals to eta minus Kk, that is Cramer's constant. Here that was Huggins constant Kh, and this is Cramer's constant Kk. Eta square C, and I've written these, that is Huggins and Cramer's equation. Okay, so this was something about intrinsic viscosity. And okay, so let's jump to the absolute viscosity. Absolute viscosity is denoted by eta, simply eta. It depends on the density of the polymeric solution with per unit flow time of the liquid, right? And it is denoted by eta. Eta equals to rho beta T. Now what is rho? Rho is the density, beta is the calibration constant, and T is the flow time of the liquid. So with the help of this, you will be able to find out eta, that is the absolute viscosity. And this is the calibration constant, which will be calculated when, how and when, I will explain you in my next lecture. So this was something very interesting today, which I've explained, which I've discussed with you. I hope you will find this video interesting, and you will have some idea about viscosity and how does it goes on, and what is dilute solution viscosity, right? So you have also, I mean, had a little knowledge about that. What are the different parameters that would be helpful to calculate, I mean, this viscosity of polymeric solutions. And I showed you an example of consistency of the flow, or the flow of honey as compared to water. And then I gave you a little bit introduction also about what is viscosity, what are the types, and what it actually means, right? So these are all the very important and very interesting aspects of viscosity, which we just shared today. So I hope you find this video interesting, and you will now start learning this viscometric process. How does it goes on? What is viscosity? How you will calculate the viscosity of polymeric compounds, and because I'll be discussing with you or sharing with you how to calculate viscosity of polymers, ship-based polymers, polymeric resins. How you will calculate there are, I mean, bunches and bunches of formulas which you will apply, and you're going to calculate the viscosity of all these polymer compounds. And I will explain you in my next video how to calibrate your viscometer, because the calibration is a must. And after going through the process of washing and rinsing, and then of course you need to calibrate your viscometer before you will introduce your solvent inside it, and you will measure the viscosity of your solvent. You need to calibrate your viscometer before that. And for that, you will fill your viscometer with some sort of a 15 ml water, some sort of water. Of course, water will be added into it. So water you will add, and you will calibrate it. And in that sense, you will be able to do the calibration, which I will explain it to you in my next video. So I hope you now have a little knowledge about viscosity and all that is about, viscosity and its parameters, different parameters, right? And of course, the different equations I've explained to you. and the different types of viscosity. There is relative viscosity, specific viscosity, inherent viscosity, reduced viscosity, intrinsic viscosity, and how you're going to plot the graph, because there are plots of, you need to plot the graphs also between reduced viscosity and concentration, between inherent viscosity and concentration. You're going to get the straight lines, and then you are going to calculate the intercepts, and you're going to find out the intrinsic viscosity. And I will explain you even how you can do it manually. How can you find out manually, calculate the intrinsic viscosity? That is also very, I mean, rare if somebody explains, but I have learned during my research journey how to do it manually without the help of an instrument. You can calculate the intrinsic viscosity of your, solvent, what you are doing in the graph. You can calculate with the help of your graph. So that was all today. Today's lecture. I hope we will again meet with something new and interesting. And of course, I would like to continue viscosity with you people, because I've started this topic, so I need to make you understand it more with more examples and with more, in some such a little bit more detail, that would help you in analyzing viscosity, analyzing you to calculate your compounds, your synthesized compounds viscosities. So thank you very much. Hopefully we'll meet again. See you next time. Have a safe life. Have a safe, I hope and pray for your good health, and because health is everything. And please stay indoors. Don't go there. Again, it's the same advice everyone is giving to each other nowadays. Don't go outside unnecessarily. COVID is everywhere, so please be careful. And let's hope for the best for the upcoming days. Goodbye.